telescope has just uncovered something that defies everything we assumed. The universe we once believed to be about 14 billion light-years wide is now understood to stretch roughly 93 billion light-years across. When the James Webb Telescope examined what looked like a blank region of space, it revealed nearly 800,000 galaxies concealed in the dark. These were galaxies that came into existence when the universe was only 300 million years old. Black holes appeared that were billions of times heavier than theory allows. Enormous structures spanned tens of millions of light-years at a time when there simply shouldn't have been enough time for them to form. Our understanding of the universe's scale was fundamentally flawed. If you're ready to discover what's truly out there, like this video and subscribe. Let's begin. The light from this galaxy departed just 280 million years after the Big Bang. It crossed expanding space for more than 13 billion years before reaching us. James Webb recorded it. The galaxy is called MOM Z14, and in 2025 astronomers verified its distance. This single observation pushed our window on the cosmos back to an era when everything was still assembling, unfinished, chaotic, astonishingly young. Here's why this is so mind-bending. The universe today is 13.8 billion years old. MOM Z14 existed when only about 2% of that history had elapsed. Consider that proportion. If the entire lifespan of the universe were compressed into one calendar year, this galaxy would have formed around January 7th. We are witnessing the universe in its infancy. This discovery was possible because James Webb works unlike earlier telescopes. It searches for what's known as redshift. As light travels across immense cosmic distances, space itself expands. That expansion stretches the light, shifting it from visible wavelengths into infrared. The farther the source, the more extreme the stretching. MOM Z14 shows a redshift of 14, 44, an indicator of staggering distance. It surpassed the previous record by only 10 million years, which sounds minor, but in the early universe, change happened at breathtaking speed. What truly astonishes researchers is that MOM Z14 isn't faint or insignificant. It shines brightly. The galaxy is in the middle of an intense burst of star formation. Its nitrogen content resembles that of ancient star clusters found in our own galaxy today, implying that stars formed in similar ways even at that early stage. According to older models, this shouldn't happen. Galaxies were expected to assemble slowly over hundreds of millions of years. MOM Z14 proves they didn't. James Webb identified it by reanalyzing existing survey images and flagging promising candidates. When astronomers noticed the faint signal, they redirected the telescope toward it in April 2025 to confirm. The spectroscopic data returned unambiguous results. No speculation, no assumptions. Solid measurements showing that this galaxy truly exists at the very edge of our observable universe. Here's the unsettling part. MOM Z14 is almost certainly not the final frontier. The Nancy Grace Roman Space Telescope is scheduled to launch in 2027. Built to scan vast regions of the sky simultaneously, it is expected to uncover galaxies from even earlier times. With every new find, the boundary moves closer to the Big Bang, and each time it does, something appears that shouldn't yet exist. Objects forming too quickly, glowing too strongly, emerging far too soon. The universe had less than 300 million years to produce MOM Z14. While 300 million years feels enormous to us, on cosmic scales it's barely a blink. For comparison, Earth has existed for 4.5 billion years. Dinosaurs roamed the planet for about 165 million years. MOM Z14 came together in less time than that. Stars ignited, gas collapsed, and structure took shape, all unfolding in the dim light of the newborn cosmos. Our long-held ideas about how galaxies form are falling apart. And this is only the start. James Webb doesn't see the universe the way human eyes do. It can't observe visible light at all. Instead, it detects infrared radiation, which is invisible to us. That design choice is exactly what gives the telescope its power to explore the early universe. Without infrared vision, none of these discoveries would have been possible. When you look at a star, you're seeing light that left it years ago. Even the nearest star beyond our sun is more than 4 light-years away, meaning its light began its journey 4 years in the past. Every glance at the night sky is a look back in time. James Webb pushes this concept to the extreme, observing objects whose light has been traveling for over 13 billion years. The telescope functions as a time machine. Infrared vision is essential because the universe is expanding. Space isn't fixed, it grows every moment. As it expands, it stretches light waves along with everything else. Radiation that began as ultraviolet or visible light is pulled into longer wavelengths. By the time it reaches us, it lies fully in the infrared. That's why objects from the early universe are invisible to telescopes limited to visible light. The Hubble Space Telescope couldn't detect galaxies like MOMSI 14 because their light had shifted beyond its range. James Webb operates from a point called Lagrange 2, about 930,000 miles from Earth. From this location, it remains permanently shielded from both Earth and the Sun, a crucial condition for its observations. Infrared detectors have to be kept at extremely low temperatures. If they warm up, they begin emitting their own infrared radiation, which overwhelms the faint signals arriving from distant galaxies. Webb's instruments operate at roughly 370 degrees Fahrenheit, colder than the surface of Pluto. The telescope's main mirror measures about 21 feet in diameter. It consists of 18 hexagon-shaped segments coated in gold. Gold is used because it reflects infrared light more efficiently than any other known material. Each segment is controlled by tiny actuators, allowing precise adjustments, so the entire mirror acts as a single, perfectly focused surface. This level of accuracy allows Webb to capture light from objects that are up to 100 times dimmer than anything Hubble could detect. This is how Webb uncovers the earliest galaxies. Astronomers program the telescope to focus on specific regions of the sky for long periods, sometimes hours, sometimes days. The longer Webb observes, the more faint light it collects. Photons that began their journey billions of years ago arrive slowly, one at a time. Webb's sensors record each one. Gradually, an image takes shape. Galaxies that would remain invisible during shorter observations emerge through extended exposure and patience. Once the light is collected, spectrograph instruments examine it in detail. They separate the light into individual wavelengths, forming what scientists call a spectrum. Every chemical element produces light at specific wavelengths, creating a distinctive signature. Hydrogen has its own pattern, different from helium. Oxygen differs from carbon. By analyzing these signatures, Webb can determine a galaxy's chemical composition, its motion, and most critically, its distance from us. The value known as redshift is extracted from these spectra. It is the essential tool for measuring how far away an object lies in the universe. What makes this unsettling is the sheer scale involved. Every deep-field image captured by Webb reveals thousands of galaxies, and each one represents a place humanity will never reach. These locations are so distant that we observe them as they existed when the universe was still very young. Imagine complete emptiness. That is how the universe appeared during its first few 100 million years. Darkness everywhere, no stars, no galaxies, only clouds of hydrogen and helium drifting through space, slowly drawn together by gravity. This period is known as the Cosmic Dark Ages, and it lasted far longer than most people realize. Then a turning point came. Gravity prevailed. Gas condensed into dense regions. Pressure increased, temperatures climbed, and the first stars ignited. That event ended the Dark Ages and marked the beginning of the cosmic dawn. MZ 14 formed during this dawn, at a time when light was just beginning to spread across the universe. 280 million years may sound like a long span. It isn't, at least not when building a galaxy. Consider what must happen. Gas clouds must collapse. Stars must form from that gas. Those stars must group together. Heavy elements must be created inside stars, a process that requires multiple stellar generations. Every stage takes time. Yet MOS 14 accomplished all of this in less than 300 million years. Here is what the universe was like then. Space itself was far smaller. Everything existed much closer together. Average temperatures were higher because matter was packed into a tighter volume. Radiation left over from the Big Bang still permeated the cosmos, though it had cooled substantially. Halos of dark matter were forming, creating gravitational traps where ordinary matter could accumulate. These halos served as invisible frameworks for the first galaxies. The gas at that time was nearly pure hydrogen and helium. There was no oxygen, no carbon, no nitrogen, none of the elements required for planets or life. Those elements first had to be created inside stars. When massive stars exploded as supernovas, they spread heavier elements into surrounding space. Later generations of stars incorporated those materials. This process, known as stellar nucleosynthesis, takes time. Many cycles, many explosions. That is what puzzles scientists. MOMS 14 already contains nitrogen. This means that at least 1 or 2 generations of stars had already formed and died within this galaxy. In under 300 million years, stars were born, consumed their fuel, exploded, enriched nearby gas, and enabled new stars to form from that enriched material. The entire sequence is compressed into an almost impossibly short time frame. Compare this to our own galaxy. The Milky Way has existed for more than 13 billion years. It has undergone countless cycles of star formation and destruction. It has built up a vast supply of heavy elements. Earth itself contains iron, silicon, gold, uranium, and many other elements that were absent in the early universe. All of them originated in ancient supernovas. MZ14 began that same process in a tiny fraction of the time, and it isn't unique. James Webb has identified more than 100 galaxies from this same early era. Each one is bright. Each one is actively forming stars. Each one contradicts models that suggested galaxies should emerge slowly. The cosmic dawn was not a gentle transition. It was a burst of intense activity. Galaxies formed rapidly, shone brightly, and transformed the universe from darkness into light within just a few 100 million years. We are only witnessing this now, over 13 billion years later, because that is how long the light needed to reach us. The implication is unsettling. The universe does not always evolve slowly and predictably. When conditions allow, it moves with astonishing speed. The forces shaping galaxies in the early universe were far more intense than anything we observe today. Inside a galaxy known as Canucks LR-86 lies a black hole unlike what current theory can explain. This galaxy existed just 570 million years after the Big Bang, which alone is remarkable. What truly defies understanding is the size of its black hole. It is supermassive, weighing millions of times more than our Sun, and it is actively feeding at a rate that exceeds theoretical limits. Black holes are typically born when massive stars collapse. A star about 20 times the mass of our Sun can explode as a supernova, leaving behind a black hole perhaps 50 times the Sun's mass. That kind of object is known as a stellar mass black hole. Compared to supermassive black holes, millions or even billions of times heavier, these are tiny. The question is how you bridge that gap. Growing from 50 solar masses to 1 million requires enormous amounts of time. A black hole must steadily consume gas, dust, and even stars over hundreds of millions or billions of years. Here lies the contradiction. Canucks LR-86 did not have that time. The universe itself was barely 500 million years old when this galaxy existed. That is nowhere near long enough for a black hole to grow to supermassive size through ordinary feeding. And yet, spectroscopy from James Webb confirms its presence. This is not a hypothesis or a guess. It is direct observational evidence. This galaxy belongs to a strange category astronomers call little red dots. These objects are compact, faint, and extremely red due to their vast distances. Since beginning operations, James Webb has uncovered dozens of them. Many puzzle scientists because they are either packed with an unrealistically high number of stars, or they host black holes that are far too massive for such small galaxies. Canucks LR-86 fits the latter case. Its black hole outweighs the combined mass of its stars by a significant margin. So how did it grow so large so quickly? There are two leading ideas. One suggests the black hole formed directly from the collapse of a massive gas cloud without ever becoming a star. This would create what researchers call a heavy seed black hole, potentially thousands of times more massive than the Sun from the start, giving it a major advantage. The second idea involves hypothetical supermassive stars, objects hundreds or thousands of times heavier than normal stars, that would collapse directly into massive black holes. Both explanations have serious issues. Direct collapse requires extremely specific conditions that may not have been widespread in the early universe. Supermassive stars remain theoretical and have never been observed. Yet the black holes exist, which means some process created them. The situation becomes even more extreme when feeding rates are considered. James Webb detected gas swirling around the black hole at extraordinary speeds. The gas is highly ionized, indicating intense radiation stripping electrons from atoms, clear evidence of rapid accretion. The black hole is consuming material more than 40 times faster than the theoretical Eddington limit, the maximum rate at which a black hole should grow before its own radiation pushes matter away. Think about what that implies. Physics predicts a hard limit on how fast black holes can feed. This one is completely ignoring it. It is devouring matter at an astonishing pace, growing far faster than models say is possible. If this continues, it will reach enormous size in a relatively short time. What unsettles scientists is what this suggests about the early universe. If Canucks LRDZ86 is not unique, if there are thousands or even millions of similar galaxies, then supermassive black holes must have formed far more quickly and easily than anyone expected. They did not need billions of years. They appeared early, aggressive, and ready to consume their surroundings. The young universe was chaotic, violent, and fast, and long-held rules about black hole growth are being rewritten as James Webb continues to peer deeper into the past. James Webb began finding these objects almost immediately. Tiny red smudges appeared throughout deep-field images. At first, astronomers assumed they were ordinary distant galaxies. Then spectroscopic data arrived, and that assumption collapsed. These objects are anything but normal. They are compact, intensely luminous, and their properties defy established models. Known collectively as little red dots, they are forcing a re-evaluation of how early galaxies evolved. So far, more than 100 have been identified. They share several defining features. They are small, much smaller than typical galaxies from the same epoch. They appear red because cosmic expansion has stretched their light. They are unusually bright for their size, and they contain either impossibly dense concentrations of stars or massive black holes that should not physically fit inside them. Here is what makes them so strange. If their brightness comes from stars alone, the required stellar density would be extreme. The stars would be packed so tightly that constant collisions and mergers would be unavoidable. Nothing like that exists in the modern universe. On the other hand, if a supermassive black hole is responsible for the brightness, then the black hole is far too large relative to its host galaxy. In galaxies today, black holes typically account for only about 0.1% of the total galactic mass. In little red dots, the black hole can be as massive as all the galaxy's stars combined. Either explanation shatters existing models. Astronomers long believed that galaxies and their central black holes evolve together in balance. First, a galaxy forms and gradually builds up its stellar population. The black hole grows more slowly, feeding on gas drifting toward the core. Over time, the two reach a stable proportion. Little red dots flip this relationship on its head. In these systems, the black hole appears to have grown first, dominating the galaxy rather than co-evolving with it. Another puzzle is how many of these objects exist. Before James Webb, scientists expected to find perhaps a few strange galaxies in the early universe. Instead, there are hundreds. They are not rare anomalies. They are common. That means the mechanism behind them was not an accident or a one-off event. It was a normal feature of how the early universe operated. Some researchers propose that little red dots are transitional objects. They may capture galaxies in the middle of an intense growth phase, where the central black hole is feeding rapidly, while the surrounding galaxy has not yet had time to build many stars. Eventually, the galaxy could catch up, forming more stars and evolving into a typical quasar, the brilliant objects powered by supermassive black holes seen across the cosmos. If this idea is correct, little red dots represent a youthful stage, a phase most galaxies pass through before reaching maturity. Others argue for a completely different formation path. Perhaps some galaxies form black holes first and assemble their stars later. Perhaps dark matter plays a much larger role than previously assumed, or perhaps conditions in the early universe allowed black holes to grow far faster than they can today. Whatever the explanation, one thing is clear: little red dots are not disappearing. Every new James Webb survey uncovers more of them. They appear at many different distances, meaning they existed throughout the universe's first billion years. They were not confined to a single moment in time. They were everywhere. The most disturbing implication lies in what they reveal about our theories. Scientists built mathematical models to explain galaxy formation. They ran simulations based on those equations. The results predicted slow, orderly growth. They showed galaxies forming stars over billions of years. They showed black holes remaining small compared to their host galaxies. Little red dots violate all three expectations. The young universe was not slow or orderly. It was violent, rapid, and extreme. Little red dots are evidence of that chaos scattered across the sky like unresolved cosmic riddles. Physics sets limits. There are strict rules governing how fast black holes can consume matter. These are not guidelines. They arise from fundamental interactions between gravity and radiation. A black hole called ELID 568 is breaking those rules entirely, and astronomers do not understand how. This black hole sits at the center of a dwarf galaxy, observed as it existed about 1.5 billion years after the Big Bang. Both James Webb and the Chandra X-ray Observatory studied it, and the data are unambiguous. LID 568 is feeding at more than 40 times the Eddington limit. The Eddington limit defines the maximum rate at which a black hole should be able to accrete matter before its own radiation pushes that matter away. Here is how it works. As material falls toward a black hole, it forms a rotating disk around the event horizon. Friction inside this disk heats the gas to millions of degrees. That hot gas emits intense radiation, including powerful X-rays. This radiation pushes outward. If matter flows in too quickly, the outward pressure becomes strong enough to repel incoming material. The black hole effectively starves itself. This creates a natural cap on growth speed. LID 568 is exceeding that cap by a factor of 40. Not slightly, not marginally, 40 times. It is like claiming a car designed to top out at 100 miles per hour is somehow traveling at 4,000. According to known physics, this should be impossible. One possible explanation is super Eddington accretion. This occurs when matter collapses inward from many directions at once, overwhelming radiation pressure through sheer mass. Trying to stop it would be like using a desk fan to halt a tidal wave. If enough gas crashes onto the black hole simultaneously, radiation simply cannot expel it fast enough. The black hole enters a short-lived feeding frenzy, consuming enormous amounts of matter in a brief burst. Such episodes are likely rare and temporary. A black hole cannot sustain super Eddington accretion for millions of years because the surrounding gas supply would be exhausted. What makes LID 568 remarkable is that astronomers observed it during this fleeting phase. It is a snapshot of runaway growth, the kind of event that could explain how supermassive black holes became so large so early in cosmic history. The black hole's mass itself is modest by supermassive standards, only a few million times that of our Sun. Given how young the universe was when LID 568 existed, that part makes sense. What does not make sense is its brightness. The energy pouring out of the accretion disk is staggering. X-rays blast into space. Nearby gas glows intensely from heat. If this feeding rate continued for only a few million years, the black hole would double its mass. Researchers believe events like this were likely common in the early universe. Gas densities were much higher then. Galaxies were still assembling, with chaotic, unstable structures. Enormous clouds of gas could collapse straight onto young black holes, triggering episodes of super Eddington feeding. Each of these bursts would rapidly add mass. Repeated over time, such events could allow a black hole to grow from stellar size to supermassive far faster than standard accretion models permit. James Webb's observation of LID 568 is crucial because it supports this idea with direct evidence. Until now, super Eddington accretion was largely theoretical. Now it has been seen, it has been measured. We know it occurs. The question is no longer whether it can happen, but how frequently it did. The universe turns out to be stranger than our equations imply. Black holes do not always obey the limits we calculate. Under the right conditions, they break them, and in the early cosmos, those conditions may have been widespread. Picture holding a single grain of sand at arm's length and looking at the sky. The tiny area that grain covers contains nearly 800,000 galaxies. That is what the Cosmos Webb survey revealed after James Webb spent more than 200 hours focused on a single region of space. The survey covered about 0.6 square degrees of sky. For comparison, the full moon spans roughly 0.2 square degrees. In other words, this survey examined an area about 3 times the apparent size of the moon. Cosmically speaking, that region is microscopic, a mere sliver of the sky. Yet within that sliver, James Webb detected a staggering number of galaxies. 800,000 systems, each containing billions or even trillions of stars. Each one lies at a different distance, meaning a different point in cosmic history. Some are relatively close, showing galaxies as they appeared not long ago. Others are so distant that their light began its journey more than 13 billion years in the past. The result is effectively a timeline of the universe, compressed into a single image. The Cosmos Webb project relied on James Webb's near-infrared camera and mid-infrared instrument to collect its data. Astronomers selected the Cosmos field because it contains very little foreground dust or nearby stars to block the view. This provides a clean window deep into space. The region had been studied for years by multiple observatories, including Hubble. But Webb's infrared sensitivity revealed vast numbers of galaxies that Hubble could not see at all. What makes this survey transformative is its balance between width and depth. Many deep-field images concentrate on extremely small areas, staring for as long as possible to detect the faintest objects. Cosmos Webb traded some depth to cover a much larger area, allowing scientists to see how galaxies are distributed across enormous scales. The result is a map showing clusters, filaments, and empty regions stretching across billions of light years. The image displays galaxies in every stage of development: spiral galaxies with graceful arms, smooth, featureless elliptical galaxies, distorted irregular systems shaped by gravitational encounters, galaxies caught in the act of merging, their structures warped as they collide, and scattered throughout are little red dots from the early universe, glowing like embers left over from the cosmic dawn. One surprising result is the sheer number of early galaxies. Before James Webb, models predicted far fewer bright galaxies within the first billion years after the Big Bang. The Cosmos Webb survey found roughly 10 times more than expected. This implies that galaxy formation was far more efficient and occurred much faster than theories suggested. The early universe was not quiet or empty. It was crowded and energetic. The survey also revealed large-scale structures forming earlier than anticipated. Groups and clusters of galaxies, systems thought to require long periods to assemble, are already present in the young universe. Gravity pulled galaxies together more quickly than predicted. The cosmic web itself, with its vast filaments and voids, was already emerging when the universe was only a few billion years old. Every galaxy in the image tells a story, each formed through a unique mix of dark matter, collapsing gas, and star formation. Some endured violent mergers, others evolved more gently over billions of years. Some are actively forming stars right now, their light dominated by hot, young, stellar populations. Others are old and dormant, shining only with the faint afterglow of long-dead stars. The Cosmos Webb survey will be analysed for years to come. Astronomers will examine individual galaxies, determine their distances, measure their chemical makeup, and track how their properties change over time. Each new study will sharpen our understanding of cosmic evolution. Each result will add another piece to the story of how the universe grew from the fireball of the Big Bang into the structured cosmos we observe today. And this is just one small patch of sky. The entire celestial sphere spans more than 40,000 square degrees. If every region contains a similar number of galaxies, then the observable universe holds more than 2 trillion of them, a number so vast that it almost stops having meaning. We cannot truly picture a number like 2 trillion. It only serves as a symbol of how unimaginably vast the universe really is. Somewhere in that immensity, a black hole is racing through space at nearly 2 million miles per hour. It is not orbiting a galaxy. It is not falling toward anything. It is fleeing, moving so fast that it drags behind it a glowing trail of newly formed stars, a cosmic wound stretching more than 200,000 light years. This black hole has a mass 10 million times greater than our Sun, making it undeniably supermassive. And yet, something struck it with enough force to eject it from its home galaxy, sending it hurtling through space at roughly 3,000 times the speed of sound. In 2025, James Webb confirmed this object, and astronomers now recognize it as the first verified runaway supermassive black hole ever observed. The object resides in what is known as the Cosmic Owl System, a group of galaxies currently in the process of merging. When galaxies collide, their central black holes usually sink toward the center of the newly formed galaxy. In rare situations, however, gravitational interactions can fling one of those black holes completely out of the system. That is exactly what occurred here. There are two known ways to expel a black hole this massive. The first involves the merger of two supermassive black holes. When they collide, they release gravitational waves that carry momentum. If those waves are emitted unevenly, the merged black hole receives a powerful recoil, much like the kickback from a firearm, launching it in a specific direction at extreme speed. These kicks can reach thousands of miles per second, fast enough to overcome a galaxy's gravitational pull. The second mechanism requires three black holes. If a galaxy already contains a binary pair of black holes and a third enters during a merger, the system becomes unstable. The interaction turns into a chaotic three-body problem with no long-term balance. One of the black holes inevitably loses the gravitational contest and is slingshot outward at tremendous velocity. James Webb identified this runaway black hole by observing a bow shock ahead of it. As the black hole barrels through intergalactic gas at incredible speed, it compresses the gas in front of it, creating a shockwave similar to the wake of a ship cutting through water. That compressed gas heats up and begins to glow. Webb also detected a long filament trailing behind the black hole, where gas has collapsed and ignited into new stars. This phenomenon has never been seen before. Star formation triggered in the wake of a fleeing supermassive black hole. As the black hole passes through space, its gravity compresses surrounding gas. That compression causes the gas to collapse, lighting up new stars along its path. The trail is visible because young stars shine brightly, emitting ultraviolet and visible light that becomes redshifted into infrared by the time it reaches us. The speed involved is staggering. At 2 million miles per hour, the black hole travels more than 500 meters every second. It could cross the distance between Earth and the Moon in under 2 minutes. Moving this fast, it will eventually escape the Cosmic Owl System entirely and roam intergalactic space as a rogue object. Galaxies without central black holes are uncommon, but this system is on the verge of becoming one. This discovery reshapes how scientists think about black hole evolution. Runaway black holes had been predicted by simulations, but observing one confirms they truly exist. It also raises new questions. If galaxy mergers frequently eject black holes, there could be thousands of rogue supermassive black holes drifting through space, invisible because they are no longer feeding on surrounding matter. The finding also implies that black hole interactions in the early universe were chaotic. During the cosmic dawn, galaxies formed and collided frequently. Their black holes would have interacted violently, some merging, others being expelled entirely. The process was disorderly, unpredictable, and left black holes scattered throughout the cosmos. James Webb's ability to detect this object highlights its extraordinary sensitivity. Neither the bow shock nor the star trail is bright. Identifying them required long exposure times and meticulous analysis, yet together they revealed something never seen before: a supermassive black hole in full retreat, racing away from its birthplace while leaving creation in its wake. In another part of the universe, two supermassive black holes are colliding inside a galaxy system known as SS7. This system existed just 740 million years after the Big Bang. Both black holes weigh millions of times more than our Sun. They are locked in orbit, spiraling closer together, destined to merge into an even larger black hole. When they do, the collision will send ripples through space-time itself. James Webb detected this merger by studying the spectrum of light coming from ZES7. The data revealed two distinct sources of intense energy located very close to one another. Both sources showed clear signs of active accretion, rapidly moving gas, extreme ionization, and broad emission lines produced by atoms swirling at tremendous speeds. The two black holes are separated by only a few thousand light years and are moving toward each other. This is the most distant black hole merger ever observed, and the earliest in the history of the universe. Mergers have been observed in the modern universe before, but never at such an early point in cosmic history. This finding confirms that black holes were already colliding and merging when the universe was less than 1 billion years old. That has profound consequences for our understanding of how supermassive black holes grew so enormous so quickly. Mergers are among the fastest possible growth mechanisms. Rather than slowly accumulating gas over millions of years, two black holes can instantly combine their mass in a single, violent event. If mergers were common in the early universe, they offer a clear explanation for how black holes reach billions of solar masses within the first billion years after the Big Bang. The merger process itself is extraordinary. As two black holes orbit one another, they emit gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. These waves carry energy away from the system, causing the orbit to shrink. The black holes spiral inward, moving faster and faster until they finally collide. The final moment lasts only a fraction of a second, yet it releases more energy than all the stars in the observable universe combined. We cannot detect the gravitational waves from ZES7 with current instruments. After traveling more than 13 billion light-years, the signal is simply too faint. Future observatories, however, will be capable of doing so. The Laser Interferometer Space Antenna, scheduled for launch in the 2030s, is designed specifically to detect gravitational waves from supermassive black hole mergers. Once operational, it will routinely observe events like ZES7. This is what makes the discovery so important. It offers a preview of what LISA will see. Before James Webb revealed mergers in the early universe, scientists believed events like ZES7 would be rare. Now it is clear they were common. That means LISA is expected to detect far more gravitational wave events than originally predicted. The merger rate in the infant universe was dramatically higher than existing models suggested. The ZS7 system also teaches us about galaxy evolution. It formed from two galaxies in the process of colliding and merging. As galaxies combine, their central black holes gradually sink toward the center of the newly formed system. This process, known as dynamical friction, occurs as black holes interact with surrounding stars and gas, losing energy and spiraling inward. Eventually, they form a binary pair that later merges. This sequence has played out throughout cosmic history. Galaxies collide frequently. The Milky Way itself is on a collision course with the Andromeda Galaxy, and the two will merge in about 4 billion years. When that happens, their central black holes will also eventually merge. The process observed in ZES7 is the same one that will unfold in our own galaxy far in the future. The gravitational waves from the ZES7 merger were emitted roughly 13 billion years ago and have been traveling through space ever since, stretching as the universe expanded. By the time LISA detects them, they will appear as long wavelength signals that only space-based observatories can measure. Those waves carry detailed information about the black holes involved, their masses, spins, and the exact dynamics of the merger. Future astronomers will extract insights from that data that James Webb alone cannot provide. Another remarkable galaxy is JD's GS140, which existed just 290 million years after the Big Bang. James Webb measured its brightness and found that it is forming stars at a rate that borders on the absurd. The galaxy is creating stellar mass about 100 times faster than theoretical models predict for such an early age. Star formation requires gas. Clouds of hydrogen collapse under gravity, compressing until temperatures reach around 10 million degrees. At that point, nuclear fusion ignites. Hydrogen fuses into helium, releasing energy, and a star is born. From start to finish, this process takes millions of years and depends on precise conditions. The gas must be dense enough, cool enough, and relatively undisturbed by turbulence. In the modern universe, galaxies form stars at a modest pace. The the Milky Way produces roughly 3 new stars per year. That may sound rapid, but compared to the hundreds of billions of stars it already contains, the rate is low. This is typical for mature galaxies. Most of their gas has either been turned into stars or blown away by stellar winds and supernova explosions. JDA's GS-140 is nothing like that. It is forming stars at a rate equivalent to hundreds or even thousands of stars per year. For a galaxy that young and relatively small, this is extreme. It means the entire system is acting like a star-forming furnace, with gas clouds collapsing almost everywhere at once. Why this is happening remains uncertain. One explanation involves cold streams of gas flowing into the galaxy from surrounding space. In the early universe, gas was arranged very differently than it is today. Dark matter, halos, created deep gravitational wells, drawing in gas from enormous distances. That gas flowed along filaments, pouring into young galaxies like rivers into a basin. This constant inflow supplied an uninterrupted source of material for rapid star formation. Another possibility is that the galaxy recently underwent a merger. When two galaxies collide, their gas clouds crash into each other, triggering enormous bursts of star formation. The impact compresses the gas, causing it to collapse on a massive scale. During these events, star formation rates can increase by factors of 10 or more. JDA's GS-140 may be observed right in the middle of such an outburst. Its brightness adds another layer of mystery. Young stars are extremely hot and luminous, producing vast amounts of ultraviolet radiation. That radiation heats nearby gas, making it glow as well. Together, these effects cause the galaxy to shine intensely. Even so, JDA's GS-140 appears brighter than expected, even after accounting for its extreme star formation rate. The amount of light suggests either that its stars are unusually massive or that an additional energy source is contributing to the glow. Some astronomers propose that supermassive stars could be involved. These hypothetical stars would be hundreds of times more massive than typical stars. They would burn extraordinarily hot and bright, surviving only a few million years before exploding. If JDA's GS-140 formed a population of such stars, their combined radiation could explain the excessive brightness. However, supermassive stars remain theoretical, with no confirmed observations to date. The galaxy's spectrum shows strong emission lines from hydrogen and oxygen, clear evidence of active star formation. These lines are broader than expected, indicating that the gas is turbulent and moving at high speeds. That turbulence may be driven by stellar winds and supernova explosions. Massive young stars live fast and die violently, injecting enormous amounts of energy into their surroundings. This energy churns the gas, creating chaotic motion throughout the galaxy. What troubles scientists most is the timing. At just 290 million years after the Big Bang, the universe had barely enough time to produce the first generation of stars, let alone assemble a galaxy undergoing extreme star formation. JDA's GS-140 should still be in its earlier stages, only beginning to take shape. Instead, it is already fully active, generating stars at an astonishing pace. This suggests that galaxy formation in the early universe was far more efficient than current models predict. Gas collapsed more rapidly. Stars formed more quickly. The feedback processes that slow star formation in modern galaxies were weaker or not yet fully established. The young universe was a far more productive environment for building galaxies. Each discovery, like JDA's GS-140, forces astronomers to rethink their assumptions. The numbers are revised, timelines are shortened, and the emerging picture of the early universe becomes more chaotic, more violent, and more impressive than anyone previously imagined. We have known since the 1920s that the universe is expanding. What remains uncertain is exactly how fast that expansion is happening. Two different measurement techniques produce two different answers, and the gap between them is too large to ignore. Astronomers call this discrepancy the Hubble tension, and James Webb has now confirmed that it is real. The expansion rate is described by a value known as the Hubble constant. It tells us how quickly galaxies move away from us depending on their distance. A value of 70 means a galaxy 1 megaparsec away is receding at 70 kilometers per second. At 2 megaparsecs, the speed doubles. Distance and recession speed scale together. There are two primary methods used to calculate this constant. The first relies on observations of the cosmic microwave background, the faint afterglow of the Big Bang. This radiation fills the universe and preserves information about conditions roughly 380,000 years after the Big Bang. By studying tiny temperature variations in this background, scientists can infer how fast the universe was expanding at that early time, and then use models to project that rate forward to today. This approach yields a Hubble constant of about 67. The second method focuses on nearby stars and galaxies. Astronomers determine distances using objects such as Cepheid variable stars and type Ia supernovae, both of which serve as reliable distance markers. By comparing those distances to how fast the galaxies are moving away, scientists directly calculate the current expansion rate. This method produces a value closer to 73. A difference of 6 units is enormous. It is not a rounding issue or a statistical fluke. Both techniques are highly precise and have been checked repeatedly, yet the discrepancy has persisted for more than 10 years. This is the Hubble tension. James Webb plays a crucial role in resolving this mystery. One concern was that earlier measurements from the Hubble Space Telescope might contain hidden errors. Perhaps distances were miscalculated, or subtle biases affected how Cepheid stars were observed. James Webb can observe the same stars with greater sensitivity and clarity. If Hubble's data were flawed, Webb would reveal different results. It did not. Webb confirmed Hubble's measurements. The distances are correct. The expansion rate measured using nearby objects truly is about 73. The tension is not caused by observational mistakes. It is real. That leaves only 2 possibilities. Either our picture of the universe is incomplete, or the way the universe expands has changed over time. The standard cosmological model assumes that cosmic expansion follows a smooth, predictable path determined by the amounts of normal matter, and dark energy. If those assumptions are even slightly wrong, the entire framework begins to fail. One possible explanation is that dark energy behaves differently than we currently believe. Dark energy is the unknown force driving the accelerated expansion of the universe. It accounts for roughly 68% of the universe's total energy content. We do not know what it is, only that it exists. If the strength of dark energy has changed over cosmic history, it could explain the discrepancy. The early universe may have expanded at one rate, while the present-day universe expands at another. Another possibility is that the universe contains an unknown component we have not yet discovered. Some new form of matter or energy that influences expansion but has so far escaped detection. Finding such a component would be revolutionary, equivalent to discovering a missing ingredient in the recipe of the cosmos. There is also the chance that the issue lies in how we interpret the cosmic microwave background. If the models used to analyze that ancient radiation are flawed, then projections from the early universe to the present would be incorrect. If the early universe behaved differently than we assume, everything built on that assumption would be skewed. The Hubble tension remains one of the most serious problems in modern cosmology. It points to a gap in our understanding. Something is missing, something unaccounted for. Until that missing piece is identified, the tension will persist, a crack running through the foundation of our cosmic models. There is a galaxy known as LAP-1b that James Webb observed during a survey searching for unusual objects in the early universe. Its spectrum came back puzzling. No oxygen, no carbon. Almost nothing except hydrogen and helium. This could be the signature of population 3 stars, the very first stars ever formed. Astronomers classify stars into populations based on their metal content. In astronomy, metals mean any element heavier than helium. Carbon is a metal. Oxygen is a metal. Iron is a metal. Modern stars contain a few percent metals by mass and are called population wine stars. Older stars contain far fewer metals, sometimes only 0.1%. These are population 2 stars. Population 3 stars would contain no metals at all, forming entirely from the pure hydrogen and helium left behind after the Big Bang. No population 3 star has ever been directly confirmed. They should have existed, but they lived and died billions of years ago. These stars were likely massive, burning through their fuel in just a few million years before exploding as supernovas. Those explosions scattered the first heavy elements into space, enriching the universe and enabling later generations of stars to form. Every star we see today, including our own, contains elements forged by population 3 stars. Finding them is extremely difficult because of their age. Any population 3 stars still visible would exist only in the most distant galaxies, observed as they were in the early universe. Their light would be faint and heavily redshifted. Even James Webb struggles to detect individual stars at such distances. Instead, astronomers search for galaxies where population 3 stars might dominate the overall stellar population. LAP-1b is one such candidate. Its spectrum shows almost no metal signatures. The light is dominated by emissions from hydrogen and helium. This could indicate a galaxy made mostly of population 3 stars. Though other explanations remain possible, the galaxy might simply contain extremely pristine gas that has not yet been enriched by supernova explosions. Or the observed spectrum could be dominated by gas clouds rather than stars. Confirming population 3 stars requires deeper observations. James Webb must observe the galaxy for longer periods, collecting more photons to reveal faint spectral details. If oxygen is truly absent, that would strengthen the case. Population 3 stars are not expected to produce much oxygen because they explode before significant amounts can form. Later generations of stars create oxygen through fusion and release it when they die. Why does this matter? Population 3 stars shaped the universe. They were the first sources of light after the cosmic dark ages. Their intense ultraviolet radiation ionized surrounding hydrogen, transforming neutral gas into plasma in a process known as rionization. This event fundamentally altered the structure of the universe. Without population 3 stars, rionization would not have occurred, and the universe would look entirely different today. These stars also laid the groundwork for everything that followed. By producing the first heavy elements, they made planets possible. Carbon, oxygen, silicon, iron, all the materials that make up Earth originated in the explosions of massive stars. Population 3 stars began that transformation. They were the universe's first alchemists, converting simple hydrogen and helium into the complex elements that make life possible. Their masses are still debated. Some models suggest they were hundreds of times more massive than our Sun. Others propose a range closer to 10 to 100 solar masses. That difference matters because it determines how they lived, how they died, and which elements they produced when they exploded. Extremely massive stars may have collapsed straight into black holes without exploding at all. If that occurred, they would not have spread heavy elements into space, delaying the enrichment needed for later generations of stars. James Webb's observation of LAP-1b offers a rare window into what the universe's very first stars may have been like. Even if this galaxy ultimately proves not to host population 3 stars, it demonstrates that Webb can identify objects pristine enough to be serious candidates. As the telescope continues probing the early universe, astronomers are confident that unmistakable evidence of these primordial giants will eventually be found. When that happens, it will complete the timeline of stellar evolution. We will have directly observed stars from every era, from the very first generation to those forming today, and will finally understand how stars transformed the universe from a simple mix of hydrogen and helium into the complex cosmos we inhabit. James Webb is also repeatedly uncovering massive galaxies within the universe's first billion years. These are not tiny proto-galaxies just igniting their first stars. They are large, developed systems containing billions of stars. According to current theory, they should not exist yet. There simply should not have been enough time for them to form. Galaxy formation is expected to be slow and orderly. Dark matter halos form first, creating gravitational wells. Gas falls into these wells over tens or hundreds of millions of years. Only after enough gas accumulates does star formation begin. A galaxy then grows gradually, adding mass through steady star formation and occasional mergers. Reaching tens of billions of stars should take at least 1 billion years. And yet James Webb has identified galaxies with those masses at redshifts of 9, 10, and even 11. These objects existed when the universe was younger than 500 million years. Some appear as early as 300 million years after the Big Bang. Their existence alone challenges the accepted timeline. One striking example is a galaxy observed at redshift 11. The data indicates it contains the equivalent of 10 billion solar masses in stars and gas. This is not a minor system. It rivals the Large Magellanic Cloud, one of the Milky Way's satellite galaxies. The problem is timing. At redshift 11, the universe was only about 400 million years old. Building 10 billion solar masses in that span would require star formation rates far beyond what current models allow. Even more puzzling, these galaxies appear mature. Their spectra reveal signs of older stellar populations, indicating that many of their stars formed earlier and have already aged. Some galaxies also show evidence of dust, which forms from material expelled by supernovae. Dust accumulation takes time. Its presence implies that these galaxies have already experienced multiple cycles of star birth and death. So how did they grow so quickly? One idea is extraordinarily efficient star formation. Perhaps the earliest galaxies converted gas into stars 10 or even 20 times more efficiently than galaxies today. If so, they could reach large masses in a short time. But this raises another question. What conditions in the early universe allowed star formation to be so efficient? Another possibility is that dark matter halos assembled faster than current simulations predict. If halos grew more rapidly, they would draw in gas sooner and in larger quantities, accelerating galaxy growth. This could point to unknown properties of dark matter or stronger early density fluctuations than we currently assume. Mergers may also have contributed. If many small galaxies formed early and merged rapidly, their combined mass could build larger systems faster than expected. Still, mergers alone are unlikely to explain the most massive galaxies. The merger rate would have to be extraordinarily high, and there simply may not have been enough time. Some researchers suggest the observations themselves might be misleading. The masses could be overestimated if unusually bright stars or active black holes are contributing extra light that mimics a larger stellar population. If that were the case, the true stellar mass would be lower, easing the tension. However, detailed spectroscopy largely rules this out. Light from stars has a distinct signature compared to light from accreting black holes, and most of these galaxies show spectra dominated by stars. The discovery of massive galaxies in the early universe is forcing astronomers to rethink how galaxies form. The equations describing structure growth may need revision. The parameters governing star formation may need adjustment. Or entirely new physics could be involved, ideas we never considered simply because we lacked observations this deep into cosmic history. Every massive early galaxy James Webb detects adds another piece to the mystery. Each one stretches the limits of what should be possible and reinforces the idea that the universe was far more dynamic, energetic, and capable of rapid growth than we ever imagined. Hold a grain of sand at arm's length against the night sky. The tiny patch it covers contains more than 10,000 galaxies. That is not an exaggeration. That is exactly what James Webb's first deep field image revealed when it focused on the galaxy cluster SMACS 0723 for 12.5 hours. The image captures a region of sky so tiny it could be hidden behind the head of a pin. Yet within that minuscule area, the universe exposes its true immensity. Galaxies fill the frame, packed tightly together, overlapping and weaving into one another. Some shine as bright spirals with well-defined shapes. Others appear as faint smears, barely separating themselves from the darkness. A handful are so distant that their light has traveled for more than 13 billion years before reaching the telescope. The galaxy cluster, SMACS 0723, lies about 4 billion light-years from Earth. It is an enormous structure made up of hundreds of galaxies bound together by gravity. The total mass of this cluster bends the fabric of space-time around it, creating a powerful gravitational lens. This lens magnifies and distorts the light from galaxies far beyond the cluster, allowing James Webb to detect objects that would otherwise be far too faint to see. Gravitational lensing is one of the universe's most effective natural tools for revealing distant objects. Einstein predicted this effect in his theory of general relativity. Massive objects curve spacetime, and light traveling through that curved spacetime follows a bent path. The effect is similar to how a glass lens bends light to focus an image. In this case, the galaxy cluster acts as a cosmic magnifier, pulling faraway galaxies into view. Some galaxies in the image appear stretched and warped into elongated arcs. These shapes are not separate objects, but single galaxies whose light has been bent around the cluster. By studying how distorted these arcs are, astronomers can estimate both the mass of the cluster and the distance of the background galaxies. Greater distortion means stronger gravity and typically greater distance. The faintest galaxies visible in the image are also the most ancient. Their light left them when the universe was less than 1 billion years old. They appear red because cosmic expansion has stretched their light over time. Radiation that began as ultraviolet has shifted into infrared wavelengths. James Webb is specifically designed to detect this infrared light, which makes it uniquely suited to uncovering the universe's earliest structures. Every galaxy in the image tells a different story. Some are young and vigorously forming stars, others are old and fading, their stellar populations slowly dying out. Some have been twisted and reshaped by mergers, others evolved quietly, untouched for billions of years. The variety is astonishing. No two galaxies are exactly alike. The deep field image also reveals the universe's large-scale structure. Galaxies are not scattered randomly through space. They gather into groups, chains and filaments that form what is known as the cosmic web. These filaments span hundreds of millions of light years, separated by vast, nearly empty voids. The SMACS 0723 cluster sits at a junction in this web, where several filaments intersect. James Webb captured this image in just 12.5 hours. The Hubble Space Telescope required weeks to reach comparable depth. This dramatic increase in efficiency allows Webb to survey much larger areas of sky in far less time, uncovering more galaxies and constructing a more complete record of cosmic history. And this image is only the beginning. Astronomers will analyze it for years, measuring individual galaxy properties, determining distances, and tracking how galaxy populations evolve. Each galaxy offers insights into star formation, chemical evolution, and the forces shaping the universe over time. What makes this image so powerful is the perspective it gives on scale. That tiny patch of sky contains thousands of galaxies. The entire sky spans more than 40,000 square degrees. If galaxy density is similar across the sky, the observable universe contains trillions of galaxies. Trillions, each potentially hosting billions of planets, each a universe of its own, filled with stars, worlds, and mysteries humanity will never reach. The grain of sand comparison is not just a metaphor, it reflects reality. The universe is so vast that the human mind cannot truly comprehend it. We can record it in images, we can describe it with numbers, but fully grasping it is beyond us. All we can do is look at these images and recognize how small our place in the cosmos truly is. Light does not travel in straight lines near massive objects. It follows the curvature of space-time, bending around concentrations of mass. This bending, gravitational lensing, turns galaxy clusters into natural telescopes that expose the most distant regions of the universe. Galaxy clusters contain thousands of galaxies, each adding to the total mass. Dark matter, which outweighs visible matter by roughly 5-to-1, contributes even more unseen mass. Together, they generate an immense gravitational field that warps space-time across millions of light years. When light from a distant galaxy passes near such a cluster, it can be deflected along multiple paths. As a result, a single background galaxy may appear several times in an image. The light travels around the cluster along different routes, reaching our telescopes from slightly different angles. Each route produces a separate image. In some cases, these images form arcs or even rings encircling the cluster. In other cases, the images appear as scattered, disconnected fragments spread across the sky. By carefully measuring the positions and shapes of these distorted images, astronomers can reconstruct the original appearance of the galaxy and calculate how far away it is. Gravitational lensing does more than distort, it also amplifies light. The bending of space-time concentrates photons, making background galaxies appear much brighter than they would without lensing. This boost can be dramatic, sometimes increasing brightness by a factor of 10 or more. Galaxies that would normally be too faint for James Webb to detect become visible because of this magnification. One well-known example is the cosmic horseshoe, a nearly complete ring created when a distant galaxy is lensed by a massive foreground cluster. The ring itself is not a physical object. It is an optical illusion, the stretched image of a single galaxy wrapped around the cluster's gravitational field. Without lensing, this galaxy would appear as a tiny, barely detectable smudge. With lensing, it becomes a striking arc spanning a large portion of the sky. James Webb actively exploits gravitational lensing to extend its reach deeper into the universe than would otherwise be possible. By observing galaxy clusters known to produce strong lensing effects, the telescope can detect galaxies from the first few 100 million years after the Big Bang. These galaxies are so distant and faint that, without lensing, even Webb would not be able to see them. Lensing does come with complications. The images it produces are warped, stretched, twisted, and sometimes broken into multiple pieces. Recovering the true shape of a galaxy requires complex modeling of the lensing cluster's mass distribution. Astronomers map the cluster's gravitational field by studying how it distorts many background galaxies. Once that field is understood, they can mathematically reverse the lensing effect and infer what the original galaxies looked like. Gravitational lensing also provides a powerful way to study dark matter. The strength of the lensing depends on the total mass along the line of sight, including matter we cannot see. By measuring how light is bent, astronomers can map the distribution of dark matter within a cluster. These maps show dense concentrations near the cluster's core, surrounded by extended halos that stretch far beyond the visible galaxies. In rare cases, lensing produces an especially striking phenomenon known as an Einstein ring. This occurs when a background galaxy, the lensing mass, and the observer are almost perfectly aligned. Light from the background galaxy bends evenly in all directions, forming a complete ring around the lens. Einstein rings are visually stunning, but they are also scientifically valuable. The size of the ring directly depends on the mass of the lens, allowing astronomers to measure that mass with high precision. The strongest gravitational lenses in the universe are galaxy clusters undergoing mergers. When clusters collide, their combined mass creates exceptionally powerful gravitational fields. These interactions generate extreme lensing effects that can magnify background galaxies by factors of 50 or more. James Webb has observed several such merging clusters, revealing galaxies that would be impossible to detect by any other means. Gravitational lensing is one of the few techniques that allows astronomers to study the universe's earliest galaxies in detail. Without it, objects from the cosmic dawn would remain hidden, too faint and too distant for even the most advanced telescopes. The universe itself has scattered natural magnifying glasses across the sky, and James Webb is using them to look farther back in time than ever before. A galaxy called Virgil appeared unremarkable in visible and ultraviolet observations, young, calm, forming stars at a modest pace. Then James Webb observed it in infrared, and the picture changed completely. At the galaxy's core lay a massive, heavily obscured, supermassive black hole releasing enormous amounts of energy. In visible light, the black hole was invisible because it was buried in thick clouds of dust. That dust absorbed the ultraviolet and visible radiation, heated up, and re-emitted the energy as infrared light, exactly the wavelength range James Webb is designed to observe. This ability to see what others cannot is one of Webb's greatest strengths. Virgil is not an isolated case. James Webb has uncovered multiple galaxies hiding active supermassive black holes. In visible light, these galaxies look quiet and ordinary. In infrared, they reveal intense activity at their centers. The black holes are feeding rapidly, pulling in gas and dust, but dense surrounding material traps the light, preventing it from escaping at shorter wavelengths. These discoveries have major consequences for our understanding of black hole populations. Earlier surveys relying on visible and ultraviolet light likely missed many active black holes. If a large fraction are concealed by dust, then the number of actively growing supermassive black holes in the universe is far higher than previously estimated. So why are so many of these black holes buried in dust? One reason is that these black holes are still in a growth phase. Young galaxies contain far more gas and dust than mature ones. The same material that feeds the black hole also hides it. As matter falls inward, the accretion disk heats up and releases enormous energy. But before that radiation can escape, it encounters clouds of dust orbiting farther out. The dust absorbs the light and re-emits it at infrared wavelengths. Geometry also plays a role. If the dusty structure around the black hole is oriented edge-on from our perspective, the dust blocks our direct view of the core. We can still see the galaxy's stars and gas, but the black hole itself remains concealed. Only infrared light, which passes through dust more easily than visible light, reveals the hidden activity. That is why infrared observations are essential for detecting objects like Virgil's black hole. Virgil's black hole is described as overmassive. Its mass is far larger than expected for a galaxy of Virgil's size. In most galaxies, the central black hole accounts for about 0.1% of the total stellar mass. In Virgil, that fraction is significantly higher. The black hole is unusually dominant, implying it grew faster than the surrounding galaxy. This challenges the traditional sequence of formation. Standard models assume galaxies form first, and black holes grow within them over time. Virgil suggests that, at least in some cases, the reverse may happen. A black hole could form early, grow rapidly, and the galaxy might assemble around it later. If this pathway exists, we should expect to find more systems like Virgil, where the black hole outweighs what the galaxy's size would suggest. This discovery also underscores the importance of observing the universe across multiple wavelengths. Studying objects in only one band of light provides an incomplete picture. In visible light, Virgil looked ordinary. In infrared, it was anything but. To understand what is really happening, astronomers need data spanning the entire electromagnetic spectrum, from radio waves to gamma rays. James Webb's mid-infrared instrument was essential for uncovering Virgil's hidden black hole. Operating between 5 and 28 micrometers, it probes wavelengths far beyond human vision. At these wavelengths, dust becomes more transparent, and the heat from buried black holes becomes detectable. How many more hidden black holes exist is still unknown. James Webb has surveyed only a tiny portion of the sky. As observations continue, many more galaxies like Virgil are likely to emerge. Each one adds another piece to the puzzle of how galaxies and black holes grow together. The universe is full of concealed structures, and many are hidden behind thick curtains of dust. James Webb is slowly pulling those curtains aside, revealing the processes that shape cosmic evolution. Our previous understanding of galaxies is changing. The picture built solely from visible light is incomplete. The new view, expanded by infrared observations, is far more complex and far more surprising than we expected. James Webb has uncovered a serious problem. Early galaxies are far too bright. Not just slightly brighter than predicted, but up to 10 times brighter. This is not a small mismatch. It points to a fundamental flaw in the models describing how galaxies formed and evolved during the universe's first billion years. Those models are highly advanced. They include dark matter, gas physics, star formation, and feedback from supernovas and black holes. Cosmologists run them on supercomputers, simulating billions of years of cosmic history. The simulations predict how many galaxies should exist at different epochs and how luminous they should be. Before James Webb, those predictions matched observations fairly well. Hubble detected early galaxies, and their numbers and brightness generally aligned with expectations. Then James Webb looked deeper, and everything changed. Galaxies appeared everywhere, far more numerous and far more luminous than the simulations allowed. So why are early galaxies so bright? One explanation is star formation efficiency. Perhaps the first galaxies converted gas into stars much more effectively than galaxies do today. If collapsing gas clouds consistently formed stars instead of being disrupted by turbulence or feedback, galaxies would build stellar mass rapidly. More stars mean more light. Another possibility involves the types of stars being formed. If early galaxies produced a larger fraction of massive stars, they would appear far brighter. Massive stars emit vastly more energy than smaller ones. A star 100 times more massive than our Sun can be up to 1,000,000 times brighter. If early stellar populations were skewed toward heavy stars, overall luminosity would rise dramatically. Supermassive stars could also play a role. These hypothetical objects would be hundreds or even thousands of times more massive than typical stars. They would shine with the output of entire galaxies, dominating the total light. Even a small number of such stars could explain the excess brightness. However, Supermassive stars remain theoretical and have not yet been confirmed. Black holes may also contribute. Actively feeding supermassive black holes release enormous amounts of energy as matter spirals inward. If early galaxies hosted more actively feeding black holes than expected, their combined emission could significantly increase a galaxy's total brightness. Some of the most luminous early galaxies do show clear signs of black hole activity, though not all of them. This brightness issue also impacts models of ionization, the era when ultraviolet radiation from the first stars ionized the universe's hydrogen gas. If early galaxies were brighter than predicted, they would have produced more ultraviolet light, potentially completing rionization sooner than models suggest. Measurements of the cosmic microwave background indicate that rionization ended roughly 400 million years after the Big Bang, and brighter early galaxies align more naturally with that timeline. Dust provides another possible explanation. Many models assume early galaxies contained very little dust because dust forms from supernova ejecta, a process thought to require time. Yet James Webb has detected dust in galaxies younger than 500 million years. If dust formed more rapidly than expected, it could alter how galaxies appear. Dust absorbs ultraviolet light and re-emits it in the infrared, reshaping a galaxy's spectrum and potentially making it appear brighter at certain wavelengths. It is also possible that the cosmological parameters themselves are slightly off. The models rely on values for dark matter density, dark energy strength, and the initial density fluctuations left by the Big Bang. If any of these numbers are incorrect, the predictions will fail. Adjusting them could bring theory closer to observation, but such changes would ripple through many other areas of cosmology. Some researchers argue the observations might be misleading. Brightness measurements could be inflated by gravitational lensing or confusion with nearer foreground objects. However, spectroscopic data largely rules this out. The redshifts are genuine, and the galaxies truly are extremely distant. The growing gap between models and observations is one of the most unexpected outcomes of James Webb's early results. It points to an incomplete understanding of how galaxies formed. Something in the early universe made galaxies brighter, faster growing, and more abundant than anticipated. Until that process is identified, the mystery remains unresolved. Light itself changes as it moves through an expanding universe. This effect is not subtle. It is the reason James Webb can observe the early cosmos at all. Without expansion stretching light into infrared wavelengths, the most distant galaxies would be permanently hidden. When a galaxy emits light, that radiation has specific wavelengths determined by atomic physics. Hydrogen produces a strong emission line at 121 nanometers in the ultraviolet. Oxygen emits characteristic lines in visible light. These wavelengths are fixed at the source, but as light travels through space, space itself expands. That expansion stretches the light waves, shifting them to longer wavelengths. Ultraviolet light becomes visible. Visible light becomes infrared. Infrared shifts into far infrared. The farther the light travels, the more it stretches. Astronomers quantify this effect using redshift, represented by the letter Z. A redshift of 1 means the wavelength has doubled. A redshift of 2 means it has tripled. MZ14, the most distant galaxy yet discovered, has a redshift of 14.44. Its light has been stretched by a factor of 15.44. Radiation that left the galaxy at about 120 nanometers now arrives at Earth near 169 nanometers, deep in the infrared. This explains why earlier telescopes could not detect such objects. The Hubble Space Telescope primarily observes visible and near-infrared light, roughly from 400 to 1,600 nanometers. Galaxies with redshifts above 7 emit most of their light, beyond Hubble's reach, and remain invisible to it. James Webb was designed specifically to overcome this limitation. Its instruments cover wavelengths from about 600 nanometers to 28,000 nanometers, spanning red visible light through the mid-infrared. This range allows Webb to detect galaxies with redshifts up to roughly 20. Beyond that, even Webb struggles, as the light shifts into wavelengths its detectors cannot register. The expansion of space is not the same as objects moving through space. It is space itself that is growing. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. not because they slide across the surface, but because the surface itself expands. Light traveling through the universe experiences the same effect. The distance between the peaks of the light wave increases as space stretches. This expansion is accelerating. Dark energy drives that acceleration, causing space to grow faster over time. As a result, galaxies far from us recede at speeds that exceed the speed of light. This does not violate relativity, because the galaxies are not moving through space faster than light. Space between us and them is expanding faster than light can traverse it. For the most distant galaxies, their light has spent more than 13 billion years traveling through this expanding universe to reach us. Over that immense span of time, the universe expanded dramatically. Space that was compact when the light first began traveling is now enormously larger. As space grew, the light waves stretched with it, transforming into infrared radiation by the time they reached James Webb's mirrors. This stretching effect is central to how astronomers measure cosmic distances. If a galaxy's redshift is known, scientists can calculate how far away it is and how long ago its light was emitted. In this way, the telescope becomes a time machine. A higher redshift means greater distance, which also means looking further back in time. The most extreme redshifts James Webb has observed lie around 14 to 15. These values correspond to galaxies seen as they existed only a few 100 million years after the Big Bang. Their light has crossed nearly 99% of the observable universe to reach us. Along the way, it was stretched by factors of 15 or more, shifting entirely out of the visible spectrum. Without this stretching, the early universe would remain hidden. Those galaxies originally emitted ultraviolet light that Earth's atmosphere blocks before it ever reaches the ground. Even ultraviolet space telescopes could not detect them because the distances are too vast and the signals too faint. Redshift converts that ultraviolet light into infrared, precisely the range where James Webb performs best. What we see then is not the universe as it originally shone, but as it appears after billions of years of transformation. Ancient light altered by cosmic expansion. Every photon captured by James Webb carries the imprint of that expansion encoded in its wavelength. There is a galaxy where the central black hole outweighs the stars, not by a small amount, but dramatically. The black hole's mass matches or exceeds the combined mass of every star in the galaxy. By conventional understanding, this should not happen. Galaxies are supposed to dominate in mass, with black holes acting as relatively small central components. Cannock's LR-36 violates that expectation. Its stars amount to only a few 100 million times the mass of our Sun, while the black hole equals or surpasses that value. The usual balance is completely reversed, as if the black hole formed first and the galaxy followed later. This relationship is known as the black hole to stellar mass ratio. In the Milky Way, the central black hole has a mass of about 4 million suns, while the galaxy's total stellar mass is roughly 60 billion suns. That produces a ratio of about 1 to 15,000. The black hole is an almost negligible fraction of the total mass. In larger galaxies, black holes can reach billions of solar masses, but the galaxies themselves also grow correspondingly larger, preserving a similar ratio. The most massive black holes typically reside in the most massive galaxies, and this relationship appears consistent across much of cosmic history, except in the early universe. James Webb has identified several galaxies, particularly among the little red dots, where black holes are far too massive for their hosts. In the first billion years after the Big Bang, the usual relationship between black hole mass and galaxy mass seems to break down. How could this occur? One explanation proposes that black holes form directly from massive gas clouds that collapsed without ever becoming stars. These direct collapse black holes would begin life already heavy, perhaps thousands or even tens of thousands of times the mass of our Sun. From that starting point, rapid accretion would allow them to grow quickly, while the surrounding galaxy built up its stars more slowly. The black hole gains an early advantage that the galaxy never overcomes. Another idea centers on supermassive stars. If the first stars were hundreds or thousands of times more massive than typical stars today, their deaths would produce unusually large black hole remnants. These massive seeds would then grow efficiently, outpacing the stellar growth of their host galaxies. A third possibility is that star formation near the black hole was suppressed. As the black hole feeds, it releases intense radiation and powerful outflows. That energy can heat surrounding gas or blow it away entirely, preventing it from collapsing into stars. In this scenario, the black hole grows by consuming gas that would otherwise form stars, naturally creating a high black hole to stellar mass ratio. The presence of overmassive black holes also helps explain the origin of modern quasars. Quasars are the brightest objects known, powered by supermassive black holes weighing billions of solar masses. Some quasars appear at redshifts as high as 7, meaning they existed when the universe was under 1 billion years old. Growing such enormous black holes so quickly requires either extreme feeding rates or very large initial seeds. If early galaxies routinely produced overmassive black holes, then the foundations for quasars were laid remarkably early. The little red dots observed by James Webb may represent quasar ancestors, captured during an early stage of evolution before their host galaxies had time to grow large enough to match the mass of their central black holes. Over time, these systems likely moved toward a more balanced state. Feedback from the black hole eventually slows its own growth by heating nearby gas and pushing it away. At the same time, the host galaxy continues pulling in gas from larger scales, steadily increasing its stellar mass. As this happens, the ratio between black hole mass and stellar mass declines, gradually approaching the proportion seen in galaxies today. What this reveals is that the growth of galaxies and black holes is not always synchronized. In the early universe, black holes sometimes surged ahead. They grew faster than their host galaxies and temporarily dominated the mass budget. This is the reverse of what we observe in the modern universe, where galaxies typically assemble first and black holes grow more slowly afterward. The universe's youth was a period of imbalance and extremes. Forces that later settled into stable relationships were still competing. Black holes held advantages they would eventually lose, and the evidence remains scattered across the sky in galaxies where black holes reign and stars play a secondary role. For hundreds of millions of years after the Big Bang, the universe was completely dark. No stars existed, no galaxies, only neutral hydrogen gas-filled space, cooling as the universe expanded. This period is known as the Cosmic Dark Ages. It ended when the first stars ignited. That moment, when light first spread through the cosmos, is called the Cosmic Dawn, occurring roughly 150 to 300 million years after the Big Bang. Gravity drew gas into dense regions. Pressure increased, temperatures climbed, nuclear fusion ignited, and the first stars began to shine. These earliest stars were unlike those we see today. They formed from pure hydrogen and helium, with no heavier elements present. That difference dramatically affected how they formed and evolved. Without metals to aid cooling, gas clouds could not fragment into small pieces. Instead, they collapsed into much larger objects. The first stars were likely between 50 and several hundred times the mass of our Sun. These massive stars burned extremely hot and bright, emitting enormous amounts of ultraviolet radiation, far more than smaller stars produce. That radiation began ionizing the surrounding hydrogen gas. Neutral hydrogen atoms absorbed ultraviolet photons, lost their electrons, and became ionized plasma. Around each star, a bubble of ionized gas formed and expanded as radiation poured outward. At first, these bubbles were isolated. Stars formed in scattered locations, each surrounded by its own ionized region, while vast stretches of space between them remained dark and neutral. As time passed, more stars formed, more ionized bubbles appeared. Eventually, the bubbles grew large enough to overlap and merge. This process is known as reionization. It transformed the universe from a cold, neutral fog into an ionized plasma. Reionization unfolded over hundreds of millions of years. Early on, only small pockets of space were ionized. By about 400 million years after the Big Bang, most of the universe had completed this transition. The cosmic dawn gave way to the cosmic noon, an era marked by intense star formation and rapid galaxy growth. James Webb is observing galaxies from this cosmic dawn period. These galaxies contain the descendants of the very first stars. A few may still host population 3 stars, though most of those primordial giants have long since died. What Webb reveals is the universe in its earliest phase of structure formation, when light was just beginning to dominate the darkness. The light from these galaxies is faint and heavily redshifted. It has traveled more than 13 billion light-years through expanding space to reach us. When that light was emitted, the universe was young and compact. Today, it is old and immense. Embedded in that ancient light is information about the conditions of the cosmic dawn, encoded in its spectrum and brightness. By studying this light, astronomers can address fundamental questions. How quickly did the first stars form? How massive were they? How efficiently did they ionize the surrounding gas? The answers shape our understanding of everything that followed. The first stars set the conditions for all later cosmic evolution. Ionization also influenced how later galaxies formed. Once the universe became ionized, small gas clumps could no longer collapse easily to form stars. Ionized gas has higher pressure, resisting gravity. This suppressed star formation in low-mass dark matter halos and prevented very small galaxies from forming. Only halos above a certain mass threshold could continue forming stars efficiently. This helps explain why there are fewer dwarf galaxies than dark matter simulations predict. Dark matter halos exist across a wide range of masses, but only the larger ones were able to host visible galaxies once the universe was ionized. The smallest halos remain dark, filled with gas that never cooled enough to ignite stars. The cosmic dawn marked a fundamental turning point. Before it, the universe was simple: hydrogen, helium, dark matter, and radiation. After it, complexity took over: stars, galaxies, heavy elements, and the vast structures we observe today. That transformation occurred in just a few 100 million years, a brief instant on cosmic timescales. James Webb is now observing the aftermath of that moment, revealing how the universe emerged from darkness into light. Every galaxy James Webb observes from the universe's first billion years carries traces of the cosmic dawn. The light from the earliest stars, long gone, shaped the galaxies we see today. Their influence is preserved in elemental abundances, in galactic structure, and in the ionization state of the gas between galaxies. In a remarkably short span of cosmic time, the universe transitioned from total darkness to widespread light. We are only now witnessing the glow of that transformation, delayed by more than 13 billion years as light crossed the expanding universe. Galaxy clusters are the largest gravitationally bound structures known. They contain hundreds or even thousands of galaxies held together by gravity. Their combined mass is staggering, equivalent to the mass of a quadrillion stars. This immense concentration of matter warps space-time so strongly that it bends the light of more distant objects, turning the cluster into a natural telescope. This phenomenon is known as strong gravitational lensing. As light from a background galaxy travels through the curved space-time surrounding a cluster, its path is deflected. From Earth, the galaxy appears distorted, magnified, and sometimes duplicated. Astronomers see elongated arcs, partial rings, or multiple images of the same object. These natural lenses allow scientists to observe galaxies that would otherwise be far too faint to detect. The gravity of the cluster focuses and amplifies the light, increasing a galaxy's brightness by factors of 10, 20, or even 50. One well-known lensing cluster is Arbel 2744, often called Pandora's cluster. Located about 3.5 billion light-years away, it contains hundreds of galaxies. Its mass distribution is especially complex because it formed from several smaller clusters merging together. That complexity produces powerful lensing effects across a wide region, making it an ideal target for deep observations. James Webb has studied Arbel 2744 extensively. Its images reveal dozens of lensed galaxies, many from the early universe. Some appear as long, stretched arcs curving across the cluster. Others show up as multiple images of the same galaxy appearing in different locations. By examining these distortions, astronomers can reconstruct the cluster's mass distribution and determine the distances, masses, and properties of the lensed galaxies. Another exceptionally strong lens is SMACS 0723, the subject of James Webb's first deep-field image. This cluster produces numerous lensing arcs clearly visible in the data. Some of those arcs correspond to galaxies with redshifts greater than 10, placing them within the universe's first half-billion years. Without the cluster's magnification, these galaxies would be beyond detection. Strong lensing requires precise alignment. The background galaxy, the lensing cluster and the observer must lie nearly along the same line of sight. When the alignment is nearly perfect, the result can be an Einstein ring, a complete circle of light surrounding the cluster. More often, the alignment is imperfect, producing partial arcs instead. Clusters also cause a subtler effect known as weak gravitational lensing. This influences galaxies that are not perfectly aligned. Their images become slightly stretched in specific directions due to the cluster's gravitational field. Individually, these distortions are hard to notice, but by statistically analyzing the shapes of many background galaxies, astronomers can map the cluster's total mass, including its dark matter component. Gravitational lensing reveals the presence of dark matter even though it emits no light. The strength of the lensing depends on the total mass along the line of sight, both visible and invisible. By comparing the lensing signal with the mass of visible galaxies, astronomers determine how much dark matter is present. The result consistently shows that dark matter outweighs ordinary matter by roughly 5 or 6 to 1. In extremely rare cases, clusters produce what is known as superlensing. This occurs when multiple clusters align along the same line of sight, each contributing to the lensing effect. The combined magnification can exceed factors of 100. Only a few such cases are known, but they allow James Webb to detect galaxies from even earlier periods in cosmic history. The drawback of gravitational lensing is distortion. To understand a galaxy's true shape and structure, astronomers must carefully model the lensing effect and mathematically reverse it. This requires detailed knowledge of the cluster's mass distribution. Research teams build sophisticated models that account for the positions and masses of individual cluster galaxies, as well as the surrounding dark matter halos. These cosmic magnifying glasses were provided by nature itself. They are not randomly distributed. Galaxy clusters form at the nodes of the cosmic web, where filaments of dark matter intersect. These intersections concentrate mass, creating the powerful gravitational fields required for lensing. By targeting such clusters, James Webb maximizes its ability to study the early universe. Nearly every major lensing cluster has now been observed by the telescope: Abell 2744, SMACS 0723, MAX 0416, and many others. Each new observation reveals additional lensed galaxies, pushing the observational boundary ever farther back in time. These clusters are accomplishing what no telescope could do on its own, pulling the universe's earlier structures into view. The light we detect from early galaxies comes from stars that no longer exist. Those stars lived, fused elements, and exploded billions of years ago. What remains is their ancient light, photons that have traveled through space for more than 13 billion years. Every photon carries information about the star that produced it. When a star forms, it emits light with a characteristic pattern. Hot, young stars shine primarily in ultraviolet and blue wavelengths. Older, cooler stars emit more red and infrared light. By examining a galaxy's spectrum, astronomers can determine stellar temperatures, ages, and chemical composition, even when the source is billions of light-years away. James Webb's spectrographs break incoming light into its individual wavelengths, producing detailed spectra. These spectra display emission lines from hydrogen, helium, oxygen, carbon, and other elements. Each element leaves a distinct fingerprint. The arrangement of these lines reveals what a galaxy is made of and how its stars are evolving. Early galaxies often show strong hydrogen and helium lines, consistent with stars forming from primordial gas. Some also show carbon and oxygen, evidence that at least one generation of stars has already lived and died, enriching the gas. Star formation is not a single event. It is continuous. Gas clouds collapse, fragment, and ignite into new stars again and again. The stars visible in James Webb images are not the first stars that formed. They are later generations, built from gas enriched by earlier supernova explosions. Each generation adds more heavy elements. The first stars, population 3, produced carbon, oxygen, and small amounts of nitrogen. When they exploded, these elements mixed into the surrounding gas. The second generation formed from this enriched material and produced heavier elements such as silicon and iron. Later generations incorporated even more metals. By the time we observe a galaxy at redshift 10, it has already undergone several stellar cycles. The stars shining at that moment are no longer pristine. They contain elements forged by earlier stars. The metal content reveals how many generations have passed. High metallicity indicates many cycles of star formation. Low metallicity suggests the galaxy is still young. The light from these stars left their galaxy when the universe was less than 500 million years old. It then traveled through expanding space for about 13.3 billion years. During that journey, the light stretched from ultraviolet wavelengths into infrared. The stars that emitted it have long since vanished. Some exploded as supernovae, others faded quietly into white dwarfs. A few collapsed into black holes. What we see is a frozen moment from the past, a galaxy captured at an early stage of its evolution. We cannot observe what happened to it afterward. If the galaxy still exists today, it is likely much larger and more evolved. It may have merged with others and transformed into something entirely different. But that future state remains unseen because the light showing it has not yet reached us. This creates a strange perspective. By observing galaxies at different distances, we see different stages of their lives. Nearby galaxies reveal what mature systems look like today. Distant galaxies show us what young systems looked like billions of years ago. By combining observations across distance, astronomers reconstruct a timeline of galaxy evolution. The stars forming in early galaxies are the ancestors of stars that exist now. The gas that created them later became part of other galaxies through mergers and accretion. Some of that gas may have ended up in the Milky Way. Some may have formed our Sun and the planets around it. The atoms in your body were forged inside stars that lived and died billions of years ago. James Webb is capturing the light from those ancient stars, photons released shortly after the cosmic dawn. Each one is a messenger from the past, carrying information about events that occurred when the universe was young. The stars are gone. The galaxies have changed. Only the light remains, traveling endlessly through space until it finally strikes a telescope mirror. Black holes face a fundamental growth limit. They cannot consume matter arbitrarily fast without stopping themselves. This restriction is known as the Eddington limit and arises from radiation pressure. As matter falls toward a black hole, it heats up and emits intense radiation. That radiation pushes outward, opposing gravity. If the radiation becomes strong enough, it blows away incoming material, capping how quickly the black hole can grow. The math is simple. A black hole with a mass of 1 million suns can increase its mass by about 1% every million years if it feeds at the Eddington limit. To grow from a stellar mass seed of roughly 100 solar masses into a billion solar mass black hole would require more than 700 million years of uninterrupted, maximum rate feeding. That barely fits within cosmic timelines, only if the black hole forms almost immediately after the Big Bang and never stops accreting. Yet James Webb has uncovered black holes with masses of hundreds of millions, even billions, of suns at redshifts greater than 7. These objects already existed when the universe was younger than 700 million years. The timing does not add up. Even if a black hole fed continuously at the maximum theoretical rate starting from a stellar mass seed, it should not have grown that large so quickly. This forces astronomers to consider two unsettling possibilities. Either black holes began their lives much heavier than expected, or they grew faster than the Eddington limit allows. Both options undermine standard models. Large initial seeds require unusual formation pathways, such as direct collapse or the death of supermassive stars. Growth beyond the Eddington limit demands special conditions that can overcome radiation pressure. One proposal suggests that some black holes form directly from collapsing gas clouds, rather than from dying stars. If a gas cloud containing tens of thousands of solar masses collapsed as a single object without fragmenting into stars, it could form a massive black hole seed. Starting at 10,000 solar masses instead of 100 dramatically shortens the time needed to reach a billion. Direct collapse, however, requires very specific conditions. The gas must be free of metals, since metals allow gas to cool and fragment into stars before a full collapse occurs. The cloud must also be bathed in intense radiation that prevents hydrogen molecules from forming. Without those molecules, cooling is inefficient and collapse proceeds as a single massive event. Such conditions may have been common early on. The first stars flooded their surroundings with ultraviolet radiation, keeping nearby gas hot. Under those conditions, collapsing clouds could have formed direct collapse black holes. If this process happened often, the early universe would have been filled with massive seeds ready to grow. Another idea involves supermassive stars. These hypothetical stars would have been hundreds or even thousands of times more massive than the Sun. They would burn their fuel extremely quickly and collapse into black holes weighing thousands of solar masses. Again, this provides a substantial head start. The difficulty with both scenarios is the lack of direct evidence. Neither direct collapse black holes nor supermassive stars have been conclusively observed. Until their formation or clear signatures are detected, they remain theoretical solutions. Super-Eddington accretion appears more grounded because it has been observed. The black hole Elid 568 feeds at more than 40 times the Eddington limit. If similar episodes were common in the early universe, black holes could gain mass far more rapidly than standard models predict. A few million years of such extreme feeding could equal tens of millions of years of normal growth. The limitation is duration. These feeding frenzies are likely brief. Once nearby gas is consumed, the rate drops. To explain rapid growth, the universe would need to supply black holes with fresh gas repeatedly and efficiently. Frequent mergers between gas-rich galaxies could provide that fuel, triggering bursts of rapid accretion. There is also a more radical possibility. Black holes might have started growing during the cosmic dark ages, before the first stars formed. If primordial black holes arose shortly after the Big Bang, they would have had extra time to grow. A black hole forming 1 million years after the Big Bang gains an additional 150 million years, compared to one forming after the first stars appeared. That extra time could make a crucial difference. Primordial black holes are controversial, requiring special early universe conditions, and most models predict they would be rare. Still, if they exist, they offer an elegant solution by extending the growth timeline. The presence of overmassive black holes is forcing theorists to re-examine long-held assumptions. Something in the early universe enabled black holes to grow at extraordinary rates. Either their seeds were heavier, their feeding was faster, or they began growing earlier than we thought. Each explanation requires revising fundamental ideas about black hole formation and evolution. James Webb's first deep field image is more than a photograph. It is a compressed history of the universe. Galaxies from different eras appear together, each at a distance that corresponds to a different moment in cosmic time. Nearby galaxies show what systems looked like a few billion years ago. The most distant ones reveal the universe as it was over 13 billion years in the past. All of that history fits into a single frame. Creating that image required 12.5 hours of continuous observation. James Webb fixed its gaze on the galaxy cluster SMACS 0723, collecting photons one by one. As exposure time increased, faint light accumulated. Galaxies invisible in short observations slowly emerged. Astronomers describe this depth using magnitude, a logarithmic scale where a difference of 5 magnitudes corresponds to a 100-fold change in brightness. The faintest objects detected in the SMACS 0723 image reach infrared magnitudes around 31. That level of faintness is about 100 million times dimmer than the faintest stars visible to the naked eye under ideal conditions. At such extreme depths, nearly every point of light is a galaxy. Individual stars are far too faint to be detected at these distances. What appear as tiny dots or soft smudges are entire galaxies, each containing billions of stars. The total number of galaxies visible in the image approaches 10,000, each one a complete system separated from us by unimaginable distances. The image reveals remarkable structural diversity. Spiral galaxies with clearly defined arms sit alongside smooth, featureless elliptical galaxies. Irregular galaxies display chaotic shapes, while merging systems are caught mid-collision. Every major galaxy type is present, highlighting the many evolutionary paths galaxies can follow. Color in the image reflects wavelength. Blue tones correspond to shorter infrared wavelengths, while red tones represent longer ones. A galaxy's color provides a clue to its distance. Nearby galaxies appear bluer because their light has experienced less stretching. Distant galaxies appear redder due to stronger redshift. The reddest objects are the most remote, dating back to a time when the universe was under 1 billion years old. Some galaxies appear multiple times because of gravitational lensing. The mass of the foreground cluster bends light from background galaxies, creating duplicated images. These duplicates often appear as arcs or distorted shapes surrounding the cluster's core. By measuring the separation and distortion of these images, astronomers can calculate the cluster's total mass, including its dark matter component. The image also includes galaxies that belong to the cluster itself. These are the bright, large galaxies near the center of the frame, located about 4 billion light-years away. They are much closer than the lensed background galaxies. The cluster formed through the gradual merging of smaller galaxy groups over billions of years, and its current appearance reflects a mature, massive structure. Between the cluster galaxies and the most distant objects lie systems at intermediate distances. These galaxies existed between roughly 4 and 12 billion years ago. They reveal what galaxies looked like at different stages of their evolution. Some are actively forming stars, glowing with youthful energy. Others have largely ceased star formation and are slowly fading. Together, they illustrate how galaxy populations change over cosmic time. What makes this image historically important is that it surpassed all previous deep field observations in both depth and area. Hubble's deepest images required weeks of exposure and covered smaller regions of sky. James Webb achieved comparable depth in just hours, opening the door to mapping much larger areas with the same sensitivity. The real power of the image lies in statistics. With thousands of galaxies visible, astronomers can track how galaxy properties change with distance and time. They can count how many galaxies existed at different epochs and examine how their shapes and brightness evolved. These measurements place strong constraints on models of galaxy formation and test fundamental cosmological theories. Every galaxy in the image has a story that can never be fully reconstructed. We observe each one at a single moment in its life, frozen by the finite speed of light. We cannot see what came before or what followed. We cannot watch their evolution unfold. All we have is this single frame, a snapshot from a cosmic film spanning billions of years. The deep field also puts our place in perspective. We are observers on a small planet, looking out at structures so vast they defy intuition. The light from these galaxies has traveled longer than humanity has existed. It began its journey when the universe was young and arrives now to be captured by instruments built from atoms forged in ancient stars. Every few months, James Webb pushes its own distance record. A galaxy is identified at redshift 13, then 14, then 1444. Each discovery extends our view deeper into the past, closer to the Big Bang. The progression feels relentless, as though there is no clear limit to how far back we can see. Redshift measures how much light has been stretched by the universe's expansion. Higher redshift corresponds to greater distance and earlier cosmic time. A redshift of 1 means looking back about 7.7 billion years. A redshift of 6 corresponds to roughly 12.7 billion years ago, when the universe was only around 800 million years old. A redshift of 14 takes us back to about 280 million years after the Big Bang. Each step to higher redshift becomes increasingly difficult. Finding galaxies at redshift 0 or 1 is relatively straightforward, as many exist at those distances. Pushing from redshift 13 to 14 is far more challenging. Galaxies are extremely rare at those epochs, and their light is extraordinarily faint. Detecting them requires surveying wide areas of sky or staring at small regions for very long periods. The current record holder is MOMS F14 at a redshift of 1444. It was not the first object suspected to lie at extreme distance. Several candidates showed similar colors, hinting at very high redshifts. However, MOMS 14 was the first to have its distance confirmed through spectroscopy. Without spectroscopic measurements, redshift estimates remain uncertain. An object that looks extremely distant based on its color alone could, in fact, be a closer galaxy with unusual physical properties. Color by itself is not definitive. True confirmation requires spectroscopy. Astronomers must detect specific emission or absorption lines within the galaxy's spectrum. These lines correspond to known elements and have precise rest frame wavelengths. By measuring how far those lines have shifted in the observed spectrum, scientists can determine exactly how much the light has been redshifted. This provides a precise and reliable distance. James Webb's near-infrared spectrograph was built for this purpose. It can observe extraordinarily faint galaxies and extract spectra even when the objects are barely visible in images. The instrument separates incoming light into hundreds of narrow wavelength channels, producing a detailed spectrum that shows exactly where key emission lines appear. Before James Webb, the highest spectroscopically confirmed redshifts were in the range of about 11 to 13, measured using Hubble and large ground-based telescopes. Those galaxies existed roughly 400 million years after the Big Bang. Webb has now pushed that boundary back by another 100 million years, reaching galaxies seen just 280 million years after the universe began. Is there a hard limit to how far back we can see? In principle, yes. The first galaxies could not form before the first stars ignited, which likely occurred around 150 to 200 million years after the Big Bang. Before that point, there were no stars and therefore no galaxies to observe. James Webb is now approaching this theoretical boundary. Pushing even twice as far would place us at the era of the very first galaxies. Finding those earliest systems, however, is extremely difficult. The universe was smaller and denser at that time, which likely means the first galaxies were smaller, dimmer, and harder to detect than those already found. Observing them requires extremely long exposure times, or surveys covering very large areas of sky. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will play a critical role by scanning far wider regions of the sky than James Webb can, increasing the chances of finding these rare objects. Every record-breaking discovery raises new questions. How did galaxies assemble so quickly? Why are they brighter than models predicted? What physical processes allowed such rapid star formation in the early universe? Each newly confirmed galaxy provides data that helps test theories and refine our understanding. The pursuit of higher redshifts is not about breaking records for their own sake. It is about probing the universe's infancy. The first galaxies laid the foundation for all later structure. They created the first heavy elements. They ionized the universe. They shaped everything that followed. Observing them directly answers some of the most fundamental questions about cosmic origins. James Webb will almost certainly continue extending the redshift record in the coming years. As more survey data is collected, astronomers will identify additional high redshift candidates. Spectroscopic observations will confirm which ones truly lie at extreme distances. Slowly, the record will move upward, inching closer to the absolute limit. Eventually, we will reach a point where no galaxies exist beyond it. At that boundary, we will be witnessing the cosmic dawn itself, the moment when the first stars ignited and light spread through the universe for the first time. James Webb has already revealed a universe far more complex and energetic than expected. Galaxies formed faster. Black holes grew larger. Large-scale structures appeared earlier. Each discovery strains existing models and forces revisions to our understanding of cosmic history. So what does all of this mean for us, for humanity and our place in this vast universe? First, it reminds us of our deep connection to cosmic history. The atoms in our bodies were forged in stars that lived and died billions of years ago. Those stars formed in galaxies like the ones James Webb now observes. The iron in our blood was created in supernova explosions. The carbon in our DNA was produced through stellar nuclear synthesis. We are, in the most literal sense, made of stardust formed in the early universe. Second, these discoveries highlight how special our moment in time is. We exist 13.8 billion years after the Big Bang in a universe that has settled and matured. The violent, chaotic conditions of the early cosmos are long past. Star formation has slowed. Galaxy mergers are less frequent. The universe today is calmer, more structured, and far more hospitable to life. Had we existed during the cosmic dawn, the environment would have been harsh and extreme. Finally, the discoveries emphasize scale. The universe contains trillions of galaxies. Each galaxy hosts billions or trillions of stars. Many of those stars have planets. The number of potentially habitable worlds is beyond comprehension. If even a tiny fraction develop life, the universe could be filled with it. We are not special in terms of location or rarity. We are one planet among countless others. And yet, we are unique in one crucial way. We are able to observe, question, and understand the universe. No other species on Earth builds telescopes or deciphers cosmic history. No other known life measures the age of the universe or traces its origins. Intelligent life capable of scientific inquiry may be common, or it may be extraordinarily rare. We do not yet know. What we do know is that we possess this capability, and we are using it to explore where we came from. Third, these discoveries highlight how much remains unknown. Dark matter accounts for most of the universe's mass, yet its nature is still a mystery. Dark energy drives cosmic expansion, but we do not understand what it is. The Hubble tension points to gaps in our cosmological model. Supermassive black holes grow faster than theory allows. Galaxies appear earlier and shine brighter than simulations predict. Each solution uncovers new problems. This is how science works. We construct models to explain what we observe. New data challenges those models. We refine them to better match reality. Then fresh observations challenge the updated versions. The cycle never ends. We move closer to truth without ever fully arriving. Every generation advances understanding, but there is always more beyond the horizon. Fourth, these findings remind us of our insignificance on a cosmic scale. We inhabit a small planet orbiting an average star in a typical galaxy located in no special region of the universe. Our galaxy is one among trillions. Our star is one of hundreds of billions within it. Earth is just one of potentially billions of habitable worlds in the Milky Way alone. The scale overwhelms us, yet that insignificance is also freeing. The universe does not center on humanity. Cosmic events follow physical laws indifferent to our existence. Black holes collide, galaxies merge, stars explode. These processes unfolded long before humans appeared, and will continue long after we are gone. We are spectators, observing a vast unfolding story that does not depend on us. Finally, these discoveries awaken a sense of wonder. Viewing images from James Webb, seeing galaxies billions of light years away, and realizing we are witnessing the universe in its youth, creates awe that goes beyond science. It reaches deeper than formulas and measurements. The universe is unimaginably vast. It is unimaginably ancient. It operates on scales of time and distance that strain human comprehension. And yet, with our tools and our minds, we have reached across billions of light years to glimpse the cosmos at its beginning. We have deciphered light emitted by ancient galaxies. We have measured the masses of black holes that formed long before Earth existed. We have traced the universe's story from the Big Bang to now. This may be humanity's greatest accomplishment, not cities or machines, but understanding our place in the cosmos. We are small. We are temporary. We are insignificant in scale, and yet we can comprehend the universe itself. That contradiction defines us. We are the universe made aware of itself. Matter arranged in a way that allows it to study matter. Atoms reflecting on atoms. James Webb has revealed a universe more strange and magnificent than expected. It has posed questions we cannot yet answer. It has uncovered structures we do not yet understand. And it has reminded us that despite our smallness, we possess the ability to explore, to discover, and to feel awe in the face of the universe's boundless immensity.